for the benefit of the recording. This is lab, I forget which lab number that is. 5?
Or is it 6? 6. Yeah, because there's 7 and we've all got one more after this one.
6. And this is the molecular weight of an acid by titration.
Okay.
Let's see, today's date is 20th, October 21.
Okay. The whole point of this lab is to determine the molecular weight of a molecule. And there are a host of different ways to determine molecular weights. It just depends on your target. In this case, we're going to determine it using titration because our target is an acid. It's citric acid. Okay? So, what do you need to know to determine molecular weight or molar mass? You need to know moles, actually mass, and how many moles that represents. That's it. So, how do you determine mass? We just weight. Right? So we get the mass, and citric acid is a solid. In order to do a titration, it's got to be in solution. So we're going to put it in water, and it's in solution. Now we need to find out how many moles there are there. So you do that by titrating with a known concentration of base. So we'll have a known concentration. Let's just, for argument's sake, say it's 1 molar sodium hydroxide. So you can titrate the base with the acid, and you find out the equivalence point. We're going to use phenolphthalein as an indicator. And you can determine when the number of equivalents of sodium hydroxide equals the number of equivalents of citric acid. And when you do that, you can relate to the number of moles that are actually over here. Okay? All we need to know is this has 1 hydroxyl per molecule. We just need to know how many hydrogens, how many acidic hydrogens are attached to this molecule. So if I say I use Ca as my abbreviation, and then I also know that there are 3 hydrogens per molecule to do that. Okay, so our reaction, our acid-base reaction would be acid plus base yields sodium with citric acid plus water. Okay, and we'll balance our equation. We've got citric acid here. If it loses 3 positives, that means it's going to be a 3 minus, right? So that means it needs 3 sodiums to balance the charge. Now we can balance here. So we need 3 of these. And we're going to need 3 of these. Okay? So we don't even have to know what the formula is for citric acid. All we need to know is how many of those are there because of the method we're using. So if we know that this is 0.1 molar, 0.1 molar, then all we need to know is what volume is it to find out how many moles we use. So let's just, for argument's sake, say there were 10 milliliters. Right? So that would be 1 millimole of sodium hydroxide was used. Right? So if this is 1 millimole of sodium hydroxide, how many millimoles of citric acid does that represent? So we just use our conversion. Sodium hydroxide on the bottom, citric acid on the top. 3 of these, 1 of those. So that's 0.33 millimoles of citric acid. Okay? But we can't use millimoles in our calculation. We got to have grams here and moles. So millimoles means 0.33 times 10 to the minus 3 moles. Then we can plug that in here. Got our answer. Okay. Problem, there's always a problem. The problem is sodium hydroxide is not stable over long periods of time. So I might create what I think is 0.1 molar sodium hydroxide, and next year it won't be that. In fact, it's always less because of the way sodium hydroxide reacts with carbon dioxide in the air. It makes sodium carbonate, which takes that out of the equation. So we need to standardize our sodium hydroxide against a known quantity of acid. And that's why we're going to use, let's see, 0.873 molar acetic acid. I don't have any here. I'll have to bring it from back up. This is stable over long periods of time. And it's delivered to us from the manufacturer. It's already been standardized. In other words, they used another method to find out this is the exact concentration. So if we know this concentration of acetic acid, then we need the equation for the two, right? One hydrogen here, one hydroxyl. So this one's easy. You just have acetic acid, and I write it this way sometimes. Like that. So there's our acidic hydrogen, and we've got sodium hydroxide, that 1,1, right? So it makes sodium acetate plus water. So if we know the number of moles, if we titrate a certain volume of this one, we measure out exact amount of volume. Actually, we measure out exact volume of this because we know that. So this is our molarity here and the volume. Right? That gives us the number of moles of this, which is equal to the number of moles of this. Now that we know exactly how many moles were delivered, we also know the volume because this is in the burette that we're using to titrate to our endpoint. So we know moles, volume, we can calculate the concentration of sodium hydroxide, and then we can use that true value for the rest of it. So we're actually going to do two things. We're going to standardize our sodium hydroxide first. Then we're going to do another titration with a known mass of citric acid. Okay. That's the whole procedure right there. Let's see, were there any pre-lab questions? Discussion questions. Yeah, discussion questions. Those are the ones that I'm supposed to go over with class. Oops. Erase that. So let's hit those two. I think there were two of them. Yeah. So, discussion questions. Number one, calculate the volume of 0.750 molar sodium hydroxide solution required to titrate 25 milliliters of 0.873 molar acetic acid solution. So what are we given? Well, as it turns out, if the number of hydroxyls per molecule is equal to the number of hydrogens per molecule of acid, you can use this relationship. Molarity of the acid times its volume equals molarity of the base times its volume. Because this equals moles and that equals moles. And if they're the same number of moles per molecule, then these are equal. Now, if they're different, then you need a different expression, normality. Okay. Normality requires that you calculate something different before you get into it. But if we've got one proton on the acid and one hydroxyl on the base, then this is a valid expression. Okay. So really all we have to do is say 0.75 molar sodium hydroxide. Yeah, 0.75 molar sodium hydroxide. And I think volume of the base is the unknown. Yeah, the volume of the base required to titrate with 25 milliliters of 0.873. There you go. So you just solve for V, for the volume of the base. Just my calculator. Oh, I didn't put it in. I didn't stick it in my scabbard. Okay, 25 times 0.873, and then divided by 0.75. So that should be, how many significant figures? Well, that was only 2. Is that right? Oh no, we got 3. 29.1 milliliters of the base. We'll do that titration. And that makes sense. This is less than that, so this has to be bigger than that. If you're doing a titration in which you've got different numbers of protons and hydroxyls in each one, then you should set up the stoichiometry and work it from that. Okay. Let's see, I can do 2 over here, I think. Calculate the volume of 0.75 molar sodium hydroxide solution required to titrate 1.20 grams of citric acid. Okay. So we've got 0.75 molar sodium hydroxide, and we've got 1.20 grams of citric acid. Okay. So for this one, we've got to know the molar mass of citric acid, don't we? Like, we can't go anywhere without moles. So is that given? We have to look it up. Maybe it's in the discussion. The accepted value for, oh, there's the equation at the bottom. So we can calculate it if we need to. I was looking to see if it was given to us already. No, we're going to have to calculate it. So the formula for citric acid is H3,657. There we go. So we just need to calculate that molar mass. And that would be your accepted value that you compare to the one you determined in class. So 3.03 for hydrogens, 6 times 12.01 for carbons, another 5.05 for the other hydrogens, and then 7 times 16. 192.14. Grams per mole. That's your accepted value. So if we convert this to moles, that would be 1.20 grams. And then we need grams on the bottom, moles on the top. So we got to divide that number into 1.20. I get 6.245. 6.245 times 10 to the minus 3 moles of citric acid. Okay, let's get back to the question. What's the volume of sodium hydroxide required? You know what I would do? Say, how many moles of protons are there? This is moles of compound. Moles of protons would be 3 times that, wouldn't it? (1.87 times 10 to the minus 2). 1.87 times 10 to the minus 2 protons. Oh, moles of protons. Moles of protons. So that many protons has to be neutralized by the same number of hydroxyls, right? So this is also equal to hydroxyls. So now we know how many moles of hydroxyls there are. Let's see. 1.87 times 10 to the minus 2 hydroxyls are required. So this is the molarity, which is moles of compound, moles of compound per liter. But since it's 1 to 1, it's also the moles of hydroxyls, is it not? Per liter. Right? So we're going to cancel. In 1 liter, we have 0.750 moles of hydroxyls. Right? You know what that means? Oh, okay. Okay. Oh, you're looking down at this. Okay. I talk too fast.
Where did the times 3 come from?
Times 3 comes from 3 protons. Right? This is moles of the compound. This makes moles of the hydrogens. Yeah. I didn't use my typical dimensional analysis. That probably would have been better if I did like this. So we have 3 protons per molecule. There we go. So that's why 3 times. And then this is the number of protons has to be equal to the number of hydroxyls, right? Because of this equation, the net equation for an acid-base reaction. 1 to 1. So if we know the number of hydrogen ions, we know the number of hydroxyls required. So now that we know the number of hydroxyls required, we find out how many milliliters that is. Well, this is liters. So we would convert it. Is that the question? How many milliliters? It just says calculate the volume. So we don't have to say milliliters, we can just say liters. Divide this number by 0.75. (2.50 times 10 to the minus 2). 2.50 times 10 to the minus 2 liters. Let's see, that would be 250. Yeah. And then 25 milliliters. Do it. That was discussion. And that's all I can think of without getting into your business. Can I race now? Okay. And what I'll do is, when Zoom sends me the MP4 file, when I process, I'll split this part out
put it under
103L. So you won't have to go digging for it.